Dark energy makes up 68% of the universe's energy density, yet we have no idea what it actually is. Einstein called his version of it his greatest blunder, but JWST observations and DESI survey data from 2025 suggest he might have been closer to the truth than anyone realized. This invisible force is accelerating the universe toward one of three possible endings: the Big Rip, heat death, or the Big Crunch. The most violent scenario literally rips apart the building blocks of reality. The most peaceful still ends with every star dying and every black hole evaporating into nothing. But recent telescope data has revealed something unexpected about this mysterious force that controls everything. The mystery force driving everything apart. The James Webb Space Telescope sent back data in 2025 that prompted researchers to refine their models of cosmic expansion. When they pointed the telescope at the most distant galaxies ever observed, they found something strange. These ancient galaxies weren't behaving the way current models predicted. The expansion rate appeared to be changing in ways that suggested dark energy itself might be evolving. DESI survey cross-checks confirmed these unexpected measurements. Think of dark energy like inflating a balloon where the rubber itself becomes stretchier the more you inflate it. The balloon doesn't just get bigger, it becomes easier to make bigger. This means the expansion doesn't slow down over time like you'd expect. Instead, it speeds up. Scientists discovered this acceleration in 1998 when two teams, the High-Z Supernova Search Team and the Supernova Cosmology Project, announced their surprise finding. They expected cosmic expansion to slow down as gravity pulled everything back together. Instead, they found expansion getting faster and faster. The force responsible for this acceleration got the name dark energy because nobody could see it, detect it, or explain what it actually was. Here's what makes this truly unsettling. Some 2025 analyses hint dark energy may strengthen over time, but this remains under debate. Most forces in physics work the opposite way. Gravity weakens with distance. Electromagnetic forces fade as objects move apart. But dark energy seems to feed on the very expansion it creates. The more space exists, the more dark energy there is to create even more space. This creates a runaway process that nothing can stop. While gravity tries to pull matter together, dark energy pushes space apart faster and faster. Right now, gravity still wins on small scales. Solar systems stay together. Galaxies hold their shape. But dark energy controls the big picture, and its influence grows stronger every moment. The 2025 observations revealed something even more disturbing. Dark energy's acceleration isn't constant. It's speeding up faster than previous models predicted. The measurements showed that the rate of acceleration itself is accelerating. This means the universe isn't just expanding faster over time. The speed at which expansion increases is also increasing. This invisible force controls the fate of everything that exists. Every atom, every star, every galaxy exists at the mercy of something we can't see, touch, or understand. Dark energy permeates every cubic centimeter of space, including the space between your atoms right now. It's actively pushing the universe apart from the inside out. The implications are staggering. If dark energy continues to strengthen, it will eventually overpower every other force in the universe. The strong nuclear force holds atomic nuclei together. The electromagnetic force binds electrons to atoms. Gravity keeps planets orbiting stars. But dark energy doesn't care about any of these forces. It just keeps making more space. Scientists have calculated three possible outcomes based on how dark energy behaves over cosmic time. In the first scenario, dark energy becomes so powerful that it literally tears apart the fabric of reality. Space expands faster than the speed of light, ripping apart galaxies, stars, planets, and eventually atoms themselves. In the second scenario, dark energy maintains its current strength, leading to a slow, cold death as the universe expands forever while matter decays. In the third scenario, dark energy weakens over time, allowing gravity to eventually win and collapse the universe back into a single point. The 2025 data suggests we're heading toward the first scenario. The measurements indicate that dark energy's influence is accelerating faster than the models predicted. Calculations suggest a threshold in tens of billions of years when dark energy overwhelms atomic forces. The timeline for cosmic destruction could be measured in tens of billions of years rather than hundreds of billions. What makes this even more remarkable is that Einstein predicted something very similar over a century ago. In 1917, he added a cosmological constant to his equations of general relativity. This constant represented a force that could push space apart to balance gravity's pull. Einstein later called this addition his greatest blunder when Edwin Hubble discovered that the universe was already expanding. But the 2025 research suggests Einstein's cosmological constant might have been his most accurate prediction. The mathematical properties of his constant match the behavior of dark energy almost perfectly. Einstein imagined a static universe where expansion balanced contraction. He never considered that this force might grow stronger over time and eventually dominate everything else. The new measurements show that dark energy behaves exactly like Einstein's cosmological constant, but with a twist. Instead of creating a static balance, it creates an accelerating expansion that grows more powerful as space itself grows. Einstein's blunder turns out to be the most important force in the universe. This discovery changes everything about how we think about cosmic evolution. Previously, scientists assumed that matter and energy would determine the universe's fate. Now they know that empty space itself contains the most powerful force in existence. The vacuum of space isn't empty. It's full of the energy that will ultimately destroy everything. The James Webb Telescope continues to gather data about distant galaxies, measuring how fast they're moving away from us. Each measurement refines our understanding of how dark energy works and how fast it's strengthening. The more scientists learn, the more they realize that dark energy is even more dominant than they originally thought. These observations have practical implications for understanding cosmic evolution. If dark energy continues to accelerate at its current rate, the universe will reach critical thresholds much sooner than expected. The forces that built every structure in the universe, from atoms to galaxies, will eventually lose their battle against the expansion of space itself. The 2025 research has narrowed down the possibilities. Scientists now have better measurements of how dark energy behaves and how fast it's strengthening. These measurements point toward a specific scenario where the universe doesn't just die. It gets torn apart piece by piece as space itself becomes hostile to the existence of matter. Understanding what happens when dark energy reaches these critical thresholds requires looking at how expansion affects different scales of reality, from the largest galaxy clusters down to individual atoms. Everything exists in a universe where space itself is actively working against the forces that hold matter together. When space itself becomes the enemy, the physics behind this cosmic tug-of-war reveals how space itself has become the enemy of matter. The space around you right now isn't empty. It looks empty, but quantum field theory predicts vacuum energy permeates all space, actively creating more space. This invisible energy fills every cubic centimeter of the universe, from the vast emptiness between galaxies to the microscopic gaps between the atoms in your body. Scientists call this phenomenon vacuum energy, and it's been working to expand the universe since the moment space and time began. This process started at the Big Bang and has never stopped. But here's where it gets strange. The expansion isn't slowing down like you'd expect. Think of it like throwing a ball versus blowing up a balloon. Gravity should slow expansion, like gravity pulls a ball back down. But dark energy accelerates expansion, like air pressure stretches balloon material. Instead of cosmic expansion gradually slowing, it speeds up. It's like throwing a ball and watching it accelerate away from you faster and faster until it disappears. The 2025 models show something that makes cosmologists nervous. The universe has been expanding at an accelerating rate for billions of years, but now it's approaching what they call a critical threshold. This threshold represents the point where expansion becomes so fast that it starts to overpower the fundamental forces that hold matter together. Previous calculations suggested this threshold was hundreds of billions of years away. Some measurements show mild disagreement with a simple constant model, suggesting the timeline might be shorter. Picture yourself on a treadmill, trying to run towards someone standing at the front of the machine. At first, the treadmill moves slowly enough that you can make progress. You might run a little slower or faster, but you're still moving forward relative to the person you're trying to reach. Now imagine the treadmill starts speeding up. You run fast or compensate, but the belt keeps accelerating. Eventually, the treadmill moves so fast that no matter how hard you run, you start moving backward relative to your target. Finally, it becomes impossible to make any forward progress at all. This analogy captures what's happening with cosmic expansion. Gravity is like your legs trying to pull matter together. Dark energy is like the treadmill belt, constantly working to push everything apart. Right now, gravity still wins on small scales. Solar systems stay together. Galaxies maintain their structure. But dark energy controls the big picture, and it's getting stronger over time. The treadmill of space expansion is speeding up, making it harder and harder for gravity to hold things together. The forces that keep atoms intact are incredibly strong. The strong nuclear force binds protons and neutrons together in atomic nuclei. The electromagnetic force holds electrons in their orbits around the nucleus. These forces are trillions of times stronger than gravity, but they operate over extremely short distances. Dark energy, on the other hand, operates over all distances and gets stronger as the universe expands. If the expansion rate continues to accelerate, it will eventually become powerful enough to overcome even these fundamental forces. This creates a terrifying possibility. Space expansion could eventually overpower the strong nuclear force and tear apart atomic nuclei. It could overcome the electromagnetic force and strip electrons away from atoms. When this happens, matter as we know it simply stops existing. The building blocks of reality get pulled apart by the expanding space between them. Galaxies in the most distant regions of the observable universe are already racing away from us faster than the speed of light. This doesn't violate Einstein's rule that nothing can move faster than light through space. Instead, space itself is expanding so fast that galaxies get carried along with it at superluminal speeds. The space between us and these distant galaxies is growing faster than light can travel across it. This expansion is happening everywhere, not just in the distant universe. The space between galaxies is expanding. The space inside galaxies is expanding. The space inside solar systems is expanding. The space between planets is expanding. The space between you and this screen is expanding. The space between the atoms in your body is expanding right now. These effects are incredibly small on local scales because gravity and the other fundamental forces are still strong enough to counteract expansion. But the expansion is relentless, and it's getting faster. The 2025 calculations reveal something unsettling about this process. Scientists have identified what they call a point of no return, where expansion becomes unstoppable. Once the universe crosses this threshold, no force in physics can prevent space from expanding faster and faster until it eventually tears apart all matter. The expansion rate would accelerate exponentially, doubling and redoubling until it overwhelms every other force in the universe. What makes this particularly disturbing is that this point of no return might be a one-way process. Once space expansion reaches critical velocity, it becomes self-reinforcing. The faster space expands, the more dark energy it contains. The more dark energy exists, the faster space expands. This creates a runaway feedback loop that nothing can stop or reverse. The implications become clear when you consider what happens to matter in this scenario. Gravity holds galaxy clusters together across millions of light years. But when space expands fast enough, even gravity can't bridge these distances anymore. Galaxy clusters dissolve as their member galaxies get stretched apart. Individual galaxies suffer the same fate as space expansion overcomes the gravitational forces holding stars together. Solar systems disintegrate next. The space between planets expands faster than gravity can pull them toward their parent stars. Planets drift away from their suns, and moons drift away from their planets. The familiar orbital mechanics that have governed celestial motion for billions of years simply stop working when space itself becomes hostile to gravitational attraction. Stars themselves start to fall apart as expansion overpowers the gravitational forces that compress stellar material. The nuclear fusion at stellar cores depends on extreme pressure created by gravity crushing matter together. When space expansion becomes strong enough, this pressure disappears. Stars can no longer maintain the conditions necessary for nuclear fusion, and they begin to dissolve. The process doesn't stop at stellar scales. Eventually, expansion becomes so rapid that it affects the forces holding atoms together. The strong nuclear force, which binds protons and neutrons in atomic nuclei, operates over distances of about 1 femtometer, roughly 1 quadrillionth of a meter. When space expands fast enough, even these tiny distances grow too large for the strong force to bridge. Atomic nuclei fall apart, leaving individual protons and neutrons scattered through expanding space. The electromagnetic force faces the same fate. Electrons orbit atomic nuclei at specific distances determined by quantum mechanics. When space expansion stretches, these distances beyond the electromagnetic force's reach, electrons detach from their atoms. Matter dissolves into a sea of isolated particles that can no longer interact with each other. This discovery fundamentally changes our understanding of a universe's fate. We're not just living in an expanding universe. We're living in a universe where space itself is actively working against the existence of matter. The expansion isn't just carrying galaxies apart. It's gradually undermining every force that allows complex structures to exist. The calculations reveal multiple pathways to cosmic destruction, each more violent than the last. The most extreme scenario doesn't just end the universe. It systematically dismantles everything that exists. The Big Rip, when reality tears apart. This violent dismantling follows a precise timeline that scientists have mapped out in disturbing detail. The universe doesn't just fade away or cool down. It gets ripped apart, piece by piece, until nothing remains but isolated particles scattered across infinite space. This isn't a gentle death. It's a violent dismantling of reality itself, where the very forces that built everything we see get overpowered by the relentless expansion of space. The timeline begins roughly 22 billion years from now. By this point, dark energy will have grown strong enough to overpower gravity on the largest scales. Galaxy clusters, which are held together by the combined gravitational pull of hundreds of galaxies, will start to stretch apart. The space between galaxies will expand faster than gravity can pull them back together. These massive structures, some spanning hundreds of millions of light years, will dissolve as their member galaxies drift away from each other. The process accelerates from there. Individual galaxies face the same fate as space expansion overwhelms the gravitational forces holding their stars together. The Milky Way, with its elegant spiral arms and central black hole, will begin to unravel. Stars that have orbited the galactic center for billions of years will find themselves pulled away from their familiar paths. The gravitational attraction that keeps stars bound to the galaxy becomes too weak to compete with the expanding space between them. Solar systems disintegrate next. The space between planets and their parent stars expands faster than gravity can bridge the distance. Earth drifts away from the sun, along with all the other planets. The orbital mechanics that have governed celestial motion since the formation of the solar system simply stop working. Planets become isolated wanderers, no longer bound to any star. Individual planets don't survive much longer. The gravitational forces that hold rocky worlds together and maintain their atmospheres get overwhelmed by space expansion. Planetary surfaces crack and crumble as the expanding space between molecules undermines the cohesive forces that keep solid matter intact. Atmospheres disperse into void as gas molecules get carried away by the stretching space between them. Stars suffer a particularly dramatic fate. These massive fusion reactors depend on gravity to compress matter in their cores to the extreme densities and temperatures necessary for nuclear fusion. When space expansion becomes strong enough, stellar gravity can no longer maintain this compression. Stars begin to swell and lose their structural integrity. The nuclear fusion that has powered them for billions of years shuts down as the stellar material gets pulled apart. The dismantling process resembles pulling apart cotton candy. Stars stretch and distort as space expansion overcomes the nuclear forces holding their matter together. The plasma that makes up stellar material gets drawn out into increasingly thin streams before finally dispersing entirely. Even the most massive stars, which normally end their lives in spectacular supernova explosions, simply dissolve as their matter gets scattered across expanding space. Ultimately, Even atoms cannot withstand the stretching space. Electrons, which orbit atomic nuclei at specific distances determined by quantum mechanics, get ripped away from their atoms. The electromagnetic force that binds electrons to nuclei operates over extremely short distances. When space expansion stretches these distances beyond electromagnetic force's reach, atoms fall apart. Matter dissolves into a sea of isolated protons, neutrons, and electrons that can no longer interact with each other. If extrapolated hypothetically, even atomic nuclei don't survive the final stages. The strong nuclear force, which binds protons and neutrons together in atomic nuclei, is the strongest force in physics, but it operates over distances of about 1 femtometer. When space expands fast enough, even these incredibly tiny distances become too large for the strong force to bridge. Protons and neutrons separate from each other, leaving behind isolated fundamental particles. The 2025 models reveal that this process, while still enormously long, could occur sooner than previously thought, in tens rather than hundreds of billions of years. Previous estimates suggested the Big Rip would unfold over much longer timescales. The new data indicates that once the process begins, it accelerates exponentially. The time between the dissolution of galaxy clusters and the tearing apart of atoms might be compressed significantly. This acceleration occurs because dark energy becomes more dominant as the universe expands. Each doubling of a universe's size doubles the amount of dark energy it contains. This creates a feedback loop where expansion accelerates the creation of more dark energy, which further accelerates expansion. The process becomes self-reinforcing, leading to exponential growth in the expansion rate. The climax arrives when space itself can expand faster than light, carrying galaxies apart. This doesn't violate Einstein's rule that nothing can move faster than light through space. Instead, space itself expands so rapidly that the distance between any two particles grows faster than light can travel between them. When this happens, particles become completely isolated from each other. No force, no interaction, no information can travel between them. The universe transforms into a collection of isolated particles scattered across infinite space. Each particle exists in complete isolation, unable to interact with any other particle in the universe. No electromagnetic signals can bridge the expanding distances. No gravitational forces can reach across the void. The particles might as well exist in separate universes, forever cut off from each other. The final state is a universe of infinite size filled with isolated particles that can never interact again. Time itself becomes meaningless because nothing can change or evolve. Each particle exists in a static state, surrounded by empty space that continues to expand forever. The universe reaches maximum entropy, where no energy differences exist to drive any kind of process or change. This scenario represents the most violent possible death for the universe. Instead of slowly cooling down or gradually running out of energy, everything gets forcibly dismantled by the expanding space between particles. The forces that created stars, planets, and life itself get systematically overpowered until nothing remains but scattered remnants that can never reunite. The Big Rip timeline depends on the exact properties of dark energy. If dark energy continues to strengthen at its current rate, this violent dismantling becomes inevitable. The 2025 measurements suggest we're on track with the scenario, but the timeline could change if dark energy behaves differently than current models predict. Yet this violent end represents just one possibility among three potential fates for the universe. The same dark energy that could tear apart reality might instead the slow death of everything. This gradual dissolution unfolds through a mechanism commonly called heat death or big freeze. The universe doesn't experience violent tearing or dramatic explosions. Instead, everything simply fades away over an incomprehensibly long time. The universe continues expanding forever, but matter remains intact throughout the process. Atoms don't get ripped apart by accelerating space expansion. Nuclear forces continue to hold protons and neutrons together. Electromagnetic forces keep electrons bound to atomic nuclei. The fundamental building blocks of reality survive, but they become increasingly useless as the universe grows larger and colder. This scenario differs fundamentally from the Big Rip. In the violent ending, space expansion overpowers the forces holding matter together, tearing apart galaxies, stars, and atoms in a cosmic dismantling process. Heat death works through a completely different mechanism. This expansion spreads matter and energy across ever-increasing volumes of space, but it never becomes powerful enough to overcome the fundamental forces that bind particles together. The key to understanding heat death lies in entropy, which measures the disorder within any system. Every system in the universe tends toward a state of highest entropy. Like a hot latte cooling to uniform temperature, the universe drives toward maximum entropy. Initially, the coffee contains concentrated thermal energy that makes it much hotter than the surrounding room. Over time, heat flows from the coffee to the cooler air around it. The coffee cools down while the room warms up slightly. Eventually, the coffee reaches the same temperature as the room, and no more heat transfer occurs. The system has reached maximum entropy, where energy is distributed as evenly as possible. The universe follows the same pattern on a cosmic scale. Right now, the universe contains regions of concentrated energy and matter. Stars burn nuclear fuel at millions of degrees, while the space between them remains near absolute zero. Galaxies cluster together in some regions, while vast voids contain almost nothing. Black holes concentrate enormous amounts of matter in tiny volumes. These energy and matter concentrations represent low-entropy states that can drive processes and create change. As the universe expands, these concentrations get diluted. The energy from stars spreads across larger volumes of space. Matter gets distributed more evenly as galaxies move farther apart. The temperature differences that allow stars to shine and planets to have weather gradually disappear. The universe slowly approaches a state where energy and matter are distributed as uniformly as possible. Even though nothing breaks in this scenario, everything still dies. Stars require fuel to maintain their nuclear fusion reactions. They consume hydrogen and helium in their cores, converting these elements into heavier elements through nuclear fusion. This process releases the energy that makes stars shine, but it also depletes the fuel supply. When stars exhaust their nuclear fuel, they die. Small stars like red dwarfs burn their fuel slowly and can survive for trillions of years. Massive stars burn through their fuel much faster and explode as supernovas after only millions of years. The 2025 observations from multiple space telescopes show that star formation is already slowing down throughout the universe. The gas clouds that collapse to form new stars are becoming more spread out as cosmic expansion carries them apart. These clouds need to reach certain densities to trigger gravitational collapse and star formation. As the universe expands, gas clouds become more diffuse and less likely to form new stars. The peak of star formation occurred billions of years ago when the universe was smaller and denser. Future generations will witness the gradual decline of stellar activity. Fewer new stars will form as gas clouds become too spread out to collapse. The existing stars will continue burning their fuel until they exhaust it and die. The universe will become progressively darker as active stars become rarer. Eventually, star formation will cease entirely when the remaining gas becomes too diffuse to collapse under its own gravity. The image of the last stars burning out evokes a profound melancholy. These final stellar remnants will shine alone in an increasingly cold and empty universe. Most galaxies will have long since gone dark, their stellar populations exhausted. The last stars will be red dwarfs, the smallest and longest-lived stars in the universe. They burn their fuel so slowly that they can survive for trillions of years after larger stars have died. But even these stellar survivors will eventually consume their fuel and fade away, leaving behind white dwarf remnants that slowly cool over cosmic time. Black holes appear to be the most permanent objects in the universe. These gravitational monsters can survive long after all the stars have died. They seem immune to the expansion and cooling that destroys other cosmic structures. But even black holes are not eternal. Stephen Hawking discovered that black holes actually evaporate over time through a process called Hawking radiation. Quantum effects near the event horizon cause black holes to slowly lose mass and energy, but only over inconceivably long timescales measured in 10⁻⁻100+ years. The final state of the universe becomes a cold, dark expanse filled with scattered particles that can never interact with each other. The temperature approaches absolute zero as energy gets spread across infinite space. Matter exists in the form of isolated electrons, protons, and photons distributed so thinly that they rarely encounter each other. No stars shine. No planets orbit. No complex structures exist. The universe reaches maximum entropy, where no energy differences remain to drive any kind of process or change. This dead universe stretches on forever with no possibility of revival. The particles continue to exist, but they cannot combine into atoms, molecules, or any other complex structures. The distances between particles grow ever larger as space continues to expand. Even if two particles somehow encountered each other, they would lack the energy necessary to interact in any meaningful way. The universe becomes a static, featureless void where nothing can happen. The timeline for heat death extends far beyond human comprehension. The process unfolds over periods measured in googles of years. By comparison, the current age of the universe is only about 14 billion years. The heat death scenario requires timescales that dwarf the entire history of cosmic evolution. Yet this slow death remains inevitable if dark energy maintains its current strength and the universe continues expanding forever. Gravity may still stage a final comeback. The force that built everything. Gravity built everything we see in the universe, from the largest galaxy clusters down to the smallest planetary systems. This fundamental force pulled together the first gas clouds that became stars, compressed stellar material until nuclear fusion ignited and gathered stars into galaxies. Every planet, every solar system, every galactic spiral arm exists because gravity won countless battles against the forces trying to pull matter apart. For billions of years, gravity has been fighting a losing war against dark energy. While gravity tries to pull everything together, dark energy pushes space apart with increasing strength. This cosmic tug-of-war determines the fate of every structure in the universe. Right now, dark energy dominates on the largest scales. Galaxy clusters drift apart as the space between them expands. Individual galaxies maintain their shape because gravity remains strong enough to hold their stars together, but they move away from each other at accelerating speeds. The battle between these opposing forces began shortly after the Big Bang. Initially, gravity had the upper hand. The universe was smaller and denser, which gave gravity more material to work with over shorter distances. During this era, gravity successfully pulled together the first stars and galaxies, creating the cosmic web we observe today. Dark energy gained strength as the universe expanded, and around 5 billion years ago became dominant enough to accelerate cosmic expansion. Since then, gravity has been fighting a losing battle on the largest scales. But this cosmic tug-of-war might not be over yet. Recent research from the Dark Energy Spectroscopic Instrument suggests that dark energy might not be constant. The DC collaboration has produced the largest 3D map of the universe to date, spanning 11 billion years of cosmic history. This challenges the standard cosmological model, which assumes dark energy remains constant throughout cosmic history. If dark energy weakens over time, gravity could eventually win the cosmic battle. Think of this process like a rubber band being stretched to its limit. When you pull a rubber band, it stretches and stores potential energy. The farther you stretch it, the more it wants to snap back. Dark energy has been stretching the universe for billions of years, but if it weakens, gravity could provide the force needed to snap everything back together. The universe would begin contracting just as it once expanded, reversing the cosmic expansion that has defined its evolution since the Big Bang. This reversal would be gradual at first. The expansion would slow down as dark energy's influence weakened and gravity's pull became more effective. Galaxy clusters would stop moving apart and begin moving toward each other. The cosmic web would start to contract as gravitational attraction overcame the expansion of space. This process would mirror the early universe in reverse, with structures getting denser and hotter as they move closer together. The contraction would become increasingly dramatic over time. As the universe became smaller and denser, gravity would become stronger and more effective at pulling matter together. The same feedback loop that made dark energy dominant would now work in gravity's favor. Smaller distances would strengthen gravitational attraction, which would pull matter closer together, which would strengthen gravity even more. The universe would enter a period of accelerating contraction. The DZ results, when combined with other datasets, predict evolving dark energy with a certainty between 2.8 to 4.2 sigma. While 5 sigma represents the gold standard for scientific certainty, these measurements provide intriguing hints that dark energy's behavior might be changing. A 3 sigma event has a 0.3% chance of being a statistical fluke. The statistical significance suggests that the observations represent real changes in dark energy's behavior rather than measurement errors. These observations hint at subtle changes in dark energy's behavior that could reshape our understanding of cosmic evolution. The standard model of cosmology assumes that dark energy, often represented by the cosmological constant, remains constant throughout time. Einstein introduced this constant in 1917 to balance gravity in his static universe model, then called it his greatest blunder after Hubble's 1929 discovery of cosmic expansion. But the DZ findings suggest that Einstein's constant might actually vary over time, meaning the universe's expansion might not continue forever. The implications extend beyond academic cosmology. If dark energy continues to weaken, the universe faces a completely different fate than the endless expansion predicted by current models. Instead of slowly cooling and spreading out until everything dies, the universe might eventually contract and heat up until everything gets compressed back into a single point. This scenario doesn't just involve the death of the universe, it involves the complete recycling of all matter and energy. Scientists remain divided about these findings. Some researchers are skeptical of the results and question whether the measurements truly indicate change in dark energy. Others are optimistic that the new data could lead to a better understanding of the fundamental physics governing the cosmos. The debate reflects the profound implications of these observations for our understanding of cosmic evolution and the ultimate fate of everything that exists. Recent observations from multiple sources support the possibility of evolving dark energy. Data from the cosmic microwave background and supernovae observations, when combined with the DAISY results, suggest that dark energy's influence has been changing over cosmic time. These independent measurements provide additional evidence that dark energy might not be the constant force that scientists originally assumed. The possibility that gravity might ultimately triumph over dark energy sets up a scenario where the universe doesn't just die, but gets completely recycled. This outcome would represent the ultimate victory of the force that built everything we see. After billions of years of losing ground to dark energy, gravity would finally win the cosmic battle and pull everything back together. The universe would face a violent but transformative ending where all matter and energy get compressed into a single point. If this scenario unfolds, the cosmic expansion we observe today would eventually reverse into something far more dramatic than simple collapse. The universe eats itself. Imagine the cosmic expansion reversing. Every galaxy in the observable universe suddenly changes direction. Instead of racing away from each other at increasing speeds, they begin moving toward each other. The cosmic expansion that has defined the universe for 13.8 billion years grinds to a halt, then reverses. Galaxies that have been separated by billions of light years start falling back together. The universe plays its entire history in reverse, contracting instead of expanding, heating up instead of cooling down. The Big Crunch unfolds in distinct phases. First, the expansion stops completely. Dark energy loses its grip on cosmic evolution and gravity takes control. The universe reaches maximum size and begins the long journey back to a single point. This reversal happens gradually at first. Galaxy clusters stop drifting apart and begin falling toward each other. The cosmic web of matter starts to contract as gravitational attraction overcomes the weakening expansion of space. As the universe becomes smaller, everything becomes denser and hotter. The cosmic microwave background radiation, which currently fills space at a frigid 2.7 degrees above absolute zero, begins to heat up. This background radiation represents the afterglow of the Big Bang, stretched and cooled by billions of years of cosmic expansion. When expansion reverses, this radiation gets compressed and blue-shifted to higher energies. The universe becomes progressively brighter as the background radiation increases in temperature. The temperature rises everywhere simultaneously. Unlike the gradual cooling that defined cosmic evolution since the Big Bang, the Big Crunch involves universal heating. There's no escape from this process. Every region of space experiences the same temperature increase as the universe contracts. The comfortable temperature differences that allow stars to shine and planets to have weather gradually disappear. The universe approaches a state of thermal equilibrium where everything reaches the same scorching temperature. Galaxy clusters begin merging in spectacular cosmic collisions. These events dwarf anything we observe in the current universe. Entire clusters containing thousands of galaxies crash into each other at incredible speeds. Individual galaxies suffer similar fates as they fall toward each other within their clusters. The Milky Way and Andromeda galaxies, which are already on a collision course, represent just one example of the galactic mergers that would occur throughout the universe. As galaxies crash together, their central black holes eventually merge, creating even more massive black holes. The cosmic collision process accelerates as the universe becomes smaller and denser. Gravitational interactions become stronger at shorter distances, pulling matter together more effectively. The same feedback loop that made dark energy dominant during expansion now works in gravity's favor. Smaller distances strengthen gravitational attraction, which pulls matter closer together, which strengthens gravity even more. The universe enters a period of accelerating contraction. Stars face a particularly strange fate during the Big Crunch. As the universe contracts, the cosmic microwave background radiation becomes hotter and more energetic. Eventually, this background radiation reaches temperatures that exceed the surface temperatures of stars. At this point, stars begin getting cooked from the outside. The radiation that once provided a cold backdrop for stellar evolution becomes hot enough to heat stellar surfaces. Stars that have burned fuel in their cores for billions of years suddenly find themselves absorbing energy from the space around them. This external heating process fundamentally changes stellar evolution. Instead of shining by converting nuclear fuel into energy, stars become net absorbers of energy from their surroundings. The universe becomes so hot that stars cannot radiate away their heat effectively. They begin to expand and lose their structural integrity as the external radiation pressure overwhelms their internal gravitational compression. Even the most massive stars, which normally maintain stable fusion reactions, start to disintegrate under these extreme conditions. Black holes emerge as the main characters in this cosmic finale. These gravitational vacuum cleaners, which spend billions of years slowly consuming matter, suddenly find themselves in an environment rich with material. As galaxies merge and stars disintegrate, black holes have access to unprecedented amounts of matter. They grow rapidly through accretion, consuming stellar debris and merging with other black holes. The universe transforms into a collection of increasingly massive black holes surrounded by hot, dense matter. The merger process continues until only the largest black holes remain. These supermassive entities, each containing the mass of millions or billions of stars, eventually encounter each other as the universe continues to contract. When supermassive black holes merge, they create gravitational waves that ripple through the fabric of space-time. These waves carry away energy and angular momentum, allowing the black holes to spiral closer together until they combine into even larger objects. The final phase involves the merger of all black holes into one supermassive entity containing everything that ever existed. This ultimate black hole represents the convergence of all matter and energy in the universe. Every atom that once formed stars, planets, and living beings gets compressed into this single gravitational monster. The black hole grows to contain the mass of the entire observable universe, compressed into a region smaller than the event horizon of current supermassive black holes. This ultimate black hole begins consuming the last remnants of space and time itself. As it approaches the size of the observable universe, the distinction between the black hole and the universe disappears. The event horizon expands to encompass all of space, creating a situation where the universe becomes indistinguishable from a black hole. Time itself becomes distorted as extreme gravitational fields affect the passage of time throughout the cosmos. The final moments arrive when this ultimate black hole reaches a critical density that mirrors the conditions present at the Big Bang. All matter and energy get compressed into a single point of infinite density called a singularity. Space and time lose their meaning as the universe collapses into this mathematical point. The laws of physics break down under these extreme conditions, just as they did at the moment of the Big Bang. Yet this violent compression might not represent the end of everything. The extreme conditions that destroy our universe could simultaneously create the conditions necessary for something entirely new to begin. The eternal cycle. The Big Crunch might not represent the death of the universe at all. Instead, it could function as a cosmic reset button, compressing all matter and energy into a single point before exploding outward in a new Big Bang. This possibility transforms our understanding of cosmic evolution from a linear story with a definitive ending to a cyclical process that repeats indefinitely. The universe we inhabit might be just one cycle in an infinite series of expansions and contractions, each following the same basic pattern but with subtle variations. The Big Bounce theory provides a framework for understanding how this cyclical process might work. Instead of collapsing into a true singularity where space and time cease to exist, the universe bounces back when it reaches maximum compression. Loop quantum cosmology suggests that space-time itself might be resilient enough to survive the extreme conditions of cosmic collapse. This theoretical framework proposes that space and time are not continuous but composed of discrete units at the smallest scales. When the universe contracts to these fundamental scales, quantum geometry creates a repulsive force that is negligible at low space-time curvature but rises rapidly in the Planck regime, overwhelming classical gravity and preventing further collapse. This quantum bridge between expanding and contracting universes eliminates the need for a true beginning or end to cosmic evolution. The universe becomes eternal, not because it expands forever, but because it undergoes endless cycles of expansion and contraction. Each cycle begins with a Big Bang, proceeds through expansion and cooling, reaches maximum size, then contracts and heats up until it bounces back into the next cycle. This process could continue indefinitely, creating a cosmos with no ultimate origin or destination. The most intriguing aspect of cyclical cosmology involves what information might carry over from one universe to the next. If the universe bounces rather than ending in a singularity, some properties from the previous cycle might influence the next one. The quantum fluctuations that seeded galaxy formation in our universe might be echoes of structures from a previous cosmic cycle. This suggests that the patterns we observe in the cosmic microwave background could contain information about universes that existed before our own Big Bang. Each cycle could be slightly different, like cosmic reincarnation with variations. Small quantum fluctuations during the bounce phase might alter the initial condition for the next expansion. These tiny changes could lead to different distributions of matter and energy, creating universes with different structures and evolutionary paths. One cycle might produce more galaxies, another might favor different types of stars, and a third might create conditions more favorable for complex chemistry and life. The laws of physics themselves might evolve between cycles. If fundamental constants like the strength of gravity or the speed of light change slightly during the bounce phase, each universe would operate under subtly different rules. This evolutionary process could lead to universes that are increasingly complex or better suited for the development of structure and life. The physical laws we observe might represent the result of countless cycles of cosmic evolution and refinement. Albert Einstein explored the possibility of cyclical universes as early as 1931, hypothesizing that there was a universe before the Big Bang that ended in a big crunch. This big crunch could create a Big Bang as a reaction, leading to an infinite cycle of expansion and contraction. Einstein briefly considered this cyclical model but lacked evidence about dark energy's dominance, which only became apparent decades later. His early intuition about cyclical cosmology has gained new support from modern quantum gravity theories that suggest spacetime might be more resilient than previously thought. The philosophical implications of cyclical cosmology center on hope rather than finality. If universes repeat infinitely, cosmic death becomes transformation rather than ending. In an infinite series of cycles, every possible arrangement of matter and energy might eventually occur. This means that universes identical to our own, or with only minor variations, could exist in other cycles. The specific combination of events that led to the formation of Earth, the evolution of life, and the development of human consciousness might repeat countless times throughout cosmic history. Recent mathematical models suggest that these cycles might be detectable in our current universe's structure. The cosmic microwave background radiation, which represents the afterglow of the Big Bang, might contain signatures of the bounce that preceded our cosmic cycle. Researchers have identified specific patterns in this radiation that could indicate whether our universe emerged from a previous contraction phase rather than from nothing. Gravitational wave detectors might also provide evidence for cyclical cosmology. The mergers of black holes and other massive objects create ripples in space-time that carry information about the universe's history. If our universe underwent a bounce phase, these gravitational waves might contain subtle signatures of the transition from contraction to expansion. The detection of such signatures would provide direct evidence for cyclical cosmology and transform our understanding of cosmic evolution. The 2025 research in loop quantum cosmology has produced detailed mathematical models of how the bounce phase might work. These models suggest that the transition from contraction to expansion occurs over a very brief period, during which quantum effects dominate over classical gravity. The bounce creates a natural mechanism for resetting the universe without requiring the complete destruction of space and time. Current observations of dark energy's behavior might provide clues about whether our universe is heading toward a bit crunch or endless expansion. If dark energy continues to weaken over time, the universe might eventually contract and undergo a bounce into the next cycle. The cyclical model offers a compelling alternative to the other two cosmic endings. Instead of facing the violent dismantling of the Big Rip or the slow decay of heat death, the universe might undergo transformation and renewal. Which of these what 2025 science actually tells us? The scientific consensus in 2025 points toward a universe dominated by dark energy, which makes up roughly 68% of all cosmic content. This invisible force drives the accelerating expansion we observe, but its exact nature remains one of physics' greatest mysteries. Multiple space missions and ground-based experiments have refined our measurements, yet each new discovery seems to raise more questions than it answers. The current data suggests we're living in a universe that's expanding faster now than it was billions of years ago, but the precise mechanisms controlling this acceleration remain unclear. The Dark Energy Spectroscopic Instrument collaboration has produced the most comprehensive map of cosmic structure ever created, tracking dark energy's influence across 11 billion years of cosmic history. This survey, involving over 900 researchers from more than 70 institutions worldwide, has analyzed nearly 15 million galaxies and quasars to understand how dark energy behaves over time. What makes these measurements particularly significant is how sensitive cosmic fate is to dark energy's properties. Small changes in how dark energy behaves over time completely alter which ending awaits the universe. The James Webb Space Telescope has revolutionized distance measurements through its infrared detectors, which can see through cosmic dust that previously obscured accurate observations. The telescope's high resolution provides what scientists call a gold standard for measuring stellar brightness, essential for calculating the Hubble constant. Recent JWST observations have confirmed earlier Hubble Space Telescope measurements while providing new precision through 3 different methods for measuring distances to galaxies that hosted supernovae. The tension between early universe measurements and late universe observations creates particular urgency around current research. As one researcher noted, this means that our simplest model of dark energy doesn't quite allow for the early universe we observe to evolve into the late universe we observe. This mismatch suggests that dark energy might be more complex than a simple constant force, potentially evolving over cosmic time in ways that could dramatically alter the universe's future. The mergers of black holes and neutron stars create ripples in the fabric of space-time that carry information about cosmic expansion rates. These measurements offer an independent way to study dark energy that doesn't rely on traditional astronomical observations. The 2025 generation of gravitational wave detectors has achieved sensitivities that allow scientists to probe cosmic expansion across different epochs of universal history. The South Pole Telescope contributes more precise constraints on cosmological models by measuring the cosmic microwave background radiation. When combined with DZ results and other datasets, these measurements reduce the likelihood that dark energy behaves like Einstein's cosmological constant. The combined data increases preference for models where dark energy evolves over time, potentially changing the predicted fate of the universe. Scientists hope upcoming missions will solve the dark energy mystery. The Nancy Grace Roman Space Telescope, set to launch by 2027, will observe supernovae and galaxy clustering patterns to measure dark energy's effects with unprecedented precision. The European Space Agency's Euclid mission aims to observe more than 1.5 billion galaxies during its 6-year prime mission, mapping how cosmic structure has evolved under dark energy's influence. Together, these missions will provide complementary datasets that should finally pin down dark energy's properties. The strengthening evidence for time-evolving dark energy represents the most significant development in 2025 cosmology. Initial hints from DZ data suggest that dark energy's influence might be weakening over time, and this evidence has grown stronger with additional analysis. The statistical significance of these findings approaches levels that would require fundamental revisions to cosmological models if confirmed. The implications extend beyond academic cosmology. If dark energy continues weakening, the universe's expansion could eventually stop or even reverse. This possibility transforms cosmic fate from inevitable heat death to potential rebirth through cyclical evolution. The difference between these scenarios depends on measurements that scientists expect to complete within the coming years. Loop quantum gravity models suggest that space-time might be more resilient than classical physics predicts. These theories propose that quantum effects could prevent the universe from reaching true singularities, potentially allowing bounces between expansion and contraction phases. If correct, these models would favor cyclical cosmology, the three endings traditionally considered. Current research suggests we're approaching a watershed moment in cosmology. The combination of JWST observations, DZ mapping, gravitational wave detections, and upcoming space missions will provide enough data to determine dark energy's true nature. The 2025 research indicates that these projects will soon test which cosmic fate awaits us. This scientific progress fundamentally changes how we understand our place in cosmic history. The measurements being made right now will determine whether we inhabit a universe destined for violent destruction, slow decay, or eternal renewal. Each possibility carries profound implications that extend far beyond the realm of physics and astronomy. The existential weight of cosmic endings. Understanding cosmic endings forces us to confront the deepest questions about existence and meaning. We are living inside a universe that is actively dying, with every moment bringing us closer to one of three possible endings. The Big Rip scenario presents perhaps the most disturbing existential challenge. In this ending, reality itself gets torn apart piece by piece. The forces that hold atoms together fail. The structures that make complex life possible disintegrate. Even the concept of together loses meaning when space expands faster than particles can interact. This violent dismantling suggests that the universe contains within itself the seeds of its own destruction. We exist in a cosmos that will eventually turn against the very matter that makes our existence possible. Heat death offers a different but equally profound challenge to meaning. Here, the universe doesn't get destroyed, it just becomes useless. Stars burn out. Black holes evaporate. Energy spreads so thin that nothing interesting can happen anymore. The universe reaches a state of maximum entropy where no change is possible. This ending suggests that all the complexity we see around us, from galaxies to ecosystems to human consciousness, represents a temporary departure from the universe's natural state of boring uniformity. The Big Crunch provides the most hopeful scenario, yet it still involves the complete destruction of everything we know. All matter gets compressed back into a single point. The universe essentially eats itself. But this ending carries the possibility of rebirth through cyclical cosmology. If the universe can bounce back from total collapse, then destruction becomes transformation rather than true ending. This scenario suggests that death and rebirth might be fundamental aspects of universal evolution. Each of these endings raises the same uncomfortable question. Does it matter how the universe ends if we won't be there to witness it? This question cuts to the heart of human meaning-making. If our species, our planet, and our entire galaxy will eventually disappear, does anything we do actually matter? The scale of temporal vastness makes human history seem like a brief flicker. Our greatest achievements and worst failures alike will be erased by the universe's ultimate fate. Recent research in 2025 has begun exploring how consciousness relates to universal death. Scientists are investigating whether consciousness might be more fundamental than previously assumed. Instead of being a byproduct of complex brain chemistry, consciousness might represent a basic feature of reality itself. This perspective suggests that the universe's ability to know itself through conscious beings might be as important as its physical evolution. The possibility that consciousness could be fundamental opens up extraordinary possibilities for surviving endings. If consciousness doesn't depend entirely on physical matter, it might find ways to persist even when the universe becomes hostile to complex structures. Advanced civilizations might discover methods to transfer consciousness to more resilient forms, or even to escape the limitations of physical reality entirely. Some scientists propose that sufficiently advanced civilizations might influence the universe's fate directly. These civilizations could potentially manipulate dark energy, alter the expansion rate, or create new forms of matter that resist destruction. The idea that intelligence might play an active role in universal evolution challenges the assumption that we are passive observers of forces beyond our control. Perhaps consciousness represents the universe's attempt to gain control over its own destiny. Different cultures and philosophies have approached endings in various ways throughout human history. Some Eastern traditions view endings as part of natural cycles, with destruction leading to renewal. Hindu cosmology describes vast cycles of creation and destruction spanning billions of years. These perspectives suggest that endings are not failures but necessary transitions in ongoing evolution. Western philosophical traditions have struggled more with the concept of ultimate endings, the idea that everything must eventually end conflicts with human desires for permanence and meaning. However, existentialist philosophers argue that awareness of universal death can actually enhance the meaning we find in existence. If our time is limited, then every moment becomes more precious. Indigenous cultures often emphasize the interconnectedness of all existence across timescales. From this perspective, universal death doesn't erase the significance of present actions because everything remains connected to everything else. The influence of conscious beings spreads throughout the cosmos in ways that transcend individual survival. The 2025 study suggests that the universe's information might be indestructible regardless of physical fate. Information theory proposes that the patterns and relationships that define reality might persist even when the matter that carries them gets destroyed. This concept relates to entropy fluctuations and Poincare recurrence theories, which suggest that given infinite time, any finite system will eventually return to its initial state. This implies that everything that ever happened, every conscious experience, every creative act might be preserved in the universe's information structure. This preservation of information provides a form of immortality that doesn't depend on physical survival. If the universe remembers everything that occurs within it, then conscious beings achieve a kind of permanence through their contributions to the information structure. Every thought, every discovery, every moment of awareness becomes part of an indestructible record. This perspective suggests that consciousness might represent the universe's method of understanding itself. Through conscious beings, the universe gains the ability to contemplate its own existence, evolution, and ultimate fate. We become the universe's way of achieving self-awareness. This role gives significance to human consciousness and intelligence. The knowledge of endings forces us to consider how we should respond to this awareness. Some people find this knowledge paralyzing, concluding that nothing matters if everything ends. Others find it liberating, realizing that perspective frees them from petty concerns and allows them to focus on what truly matters. Still others find it motivating, seeing consciousness as the universe's most remarkable achievement and feeling responsible for preserving and expanding it. The weight of endings transforms every human choice into something larger than individual consequence. In a universe destined to die, the emergence of consciousness capable of understanding that destiny might be the most remarkable phenomenon of all. This awareness creates a strange paradox that challenges everything we thought we knew about meaning and purpose. Living in a dying universe, how should we respond to this cosmic awareness? Understanding that the universe will eventually die creates a profound shift in perspective. This knowledge, which could make existence seem pointless, actually makes life more meaningful. When you realize that everything exists temporarily in a cosmos destined for one of three possible endings, every moment becomes more precious. The fact that conscious beings emerge in a universe that would outlast them by billions of years transforms human existence from an accident into something extraordinary. The 2025 research has fundamentally changed how scientists view humanity's role in cosmic evolution. Previously, humans seemed like insignificant specks in a vast, indifferent universe. Now, scientists recognize that consciousness might represent the universe's most important achievement. Through conscious beings, the cosmos gains the ability to understand its own structure, evolution, and ultimate fate. We become the universe's method of achieving self-awareness, transforming from cosmic accidents into cosmic necessities. This perspective suggests that consciousness serves as the universe's way of understanding itself. The atoms in your brain were forged in stellar cores billions of years ago. Those atoms eventually organized into structures complex enough to contemplate their own origins and the fate of everything that exists. This means the universe literally thinks about itself through human consciousness. Every scientific discovery, every philosophical insight, every moment of wonder about cosmic mysteries represents the universe gaining deeper self-understanding. The knowledge of cosmic endings has dramatically influenced current space exploration priorities. The discovery that dark energy might be changing over time has accelerated research into understanding its behavior. Scientists now know they have a limited window to solve the dark energy mystery before technological limitations make certain observations impossible. This urgency has reshaped mission planning and funding decisions across multiple space agencies. The Euclid mission and Nancy Grace Roman Space Telescope. represent humanity's most ambitious attempts to understand cosmic fate. These projects will observe billions of galaxies to map how dark energy has influenced cosmic evolution over the past 11 billion years. The missions require unprecedented international cooperation and technological innovation. Scientists expect these observations to finally determine which of the three cosmic endings awaits the universe. The Dark Energy Spectroscopic Instrument has already created the largest three-dimensional map of the universe ever made, tracking dark energy's influence across cosmic history. This massive scientific effort reflects the urgency scientists feel about understanding cosmic fate. The project represents humanity's collective attempt to understand the force that controls our ultimate destiny. The vast amounts of data generated by space missions require advanced AI algorithms for analysis and cataloging. Machine learning systems help scientists identify patterns in cosmic structure that reveal dark energy's behavior. These AI tools have become essential for processing the enormous data sets needed to understand cosmic fate. The knowledge of cosmic endings affects how we approach these technological challenges. The potential for humanity to spread consciousness throughout the cosmos before any ending occurs provides hope for transcending cosmic death. If consciousness represents the universe's way of understanding itself, then preserving and expanding awareness becomes significant. Human space exploration might represent the first step in a process that eventually fills the universe with conscious beings capable of understanding its fate. The 2025 discoveries about the universe's fate are changing education and cultural perspectives worldwide. Students learn about cosmic endings alongside traditional subjects, gaining perspective on humanity's place in the larger cosmos. This knowledge influences how people think about their daily problems and long-term goals. Understanding cosmic fate provides a framework for evaluating what matters most in human existence. Cultural perspectives are shifting as people integrate cosmic awareness into their worldviews. The knowledge that everything exists temporarily in a universe destined for death paradoxically enhances appreciation for present experiences. People report feeling more connected to others and more motivated to contribute positively to human knowledge and culture when they understand cosmic context. Educational curricula increasingly emphasize humanity's role as the universe's way of understanding itself. Students learn that scientific research and philosophical inquiry serve cosmic purposes beyond immediate practical applications. This perspective encourages young people to pursue careers in science, philosophy, and other fields that contribute to cosmic understanding. The research suggests that consciousness might be the universe's method of gaining control over its own evolution. Through conscious beings, the cosmos develops the ability to understand its own structure and potentially modify its behavior. This transforms cosmic death from an inevitable fate into a challenge that intelligence might eventually address, though such possibilities remain highly speculative. These discoveries force us to confront fundamental questions about existence and meaning. The knowledge that we live in a universe destined to die affects how we evaluate our choices and priorities. Understanding cosmic fate provides unprecedented perspective on human existence while suggesting that our actions might have consequences extending far beyond individual lifespans. The implications extend to how we think about scientific progress and human achievement. Every measurement of distant galaxies, every calculation about dark energy's behavior, every attempt to understand cosmic evolution represents the universe studying itself through conscious observers. This transforms scientific research from mere curiosity into a cosmic responsibility. The awareness of cosmic endings creates both humility and purpose. We recognize our temporary place in a vast cosmos, while simultaneously understanding that consciousness might be the most remarkable phenomenon the universe has produced. This dual perspective challenges us to consider how cosmic knowledge should influence our daily choices and long-term thinking. Living in a dying universe means accepting that nothing lasts forever while finding meaning in the temporary emergence of awareness capable of understanding that impermanence. This knowledge transforms how we approach existence itself, providing a framework for evaluating what truly matters in the brief time we have to contemplate the cosmos that created us. The 2025 observations have brought us closer to understanding which cosmic ending awaits, though significant uncertainties remain about dark energy's true nature. We cannot control the universe's ultimate fate, but understanding it gives us unprecedented perspective on our place in existence. The knowledge that we live in a dying cosmos transforms how we view our daily problems and long-term goals. This awareness makes every moment more precious, every human connection more meaningful, and every scientific discovery more significant. In our universe destined to die, the temporary emergence of consciousness capable of understanding that fate might be the most remarkable phenomenon of all. While we still debate which ending awaits, the answers may come sooner than we think. What do you think about these cosmic possibilities? Share your thoughts in the comments below, and if this perspective changed how you see existence, consider